You see, in quantum field theory, the quantum vacuum state is the lowest energy state possible. Imagine it as a vast, empty desert. But here's the twist. This desert isn't really empty. Rather, it's brimming with fleeting electromagnetic waves and particles that pop in and out of existence. This isn't just science fiction, this is the very fabric of our universe. The term zero-point field often gets thrown around as a synonym for this vacuum state. Think of it as the quiet hum of the universe, even in the absence of physical particles. Now, let's rewind to the 1930s. Quantum electrodynamics, or QED, was the first quantum field theory vacuum to be developed. Pioneers like Feynman, Tomonaga, and Schwinger took this idea and ran with it, eventually bagging a Nobel Prize in 1965 for their groundbreaking work. Fast forward to today and we have the Standard Model, an epic generalization of QED. This model includes all known elementary particles and their interactions, except gravity. One part of this model, quantum chromodynamics, or QCD, deals with strong interactions. Scientists study the QCD vacuum at colossal facilities like the Large Hadron Collider and the Relativistic Heavy Ion Collider. Here they're probing the very structure of these strong interactions. So what does this mean for the properties of the vacuum? If quantum field theory can be described through perturbation theory, the vacuum's properties resemble those of a ground state in a quantum mechanical harmonic oscillator. In simpler terms, the vacuum expectation value of any field operator vanishes, but it gets even more intriguing. In scenarios where perturbation theory fails at low energies, like in QCD or the BCS theory of superconductivity, field operators might have non-zero vacuum expectation values. These are called condensates. The Standard Model's Higgs field, for example, has a non-zero vacuum expectation value. This spontaneous symmetry-breaking mechanism is how other fields in the theory gain mass. According to Astrid Lambrecht in 2002, when one empties out a space of all matter and lowers the temperature to absolute zero, one produces in a Gedankenexperiment, that's German for thought experiment, the quantum vacuum state. But here's a twist. The third law of thermodynamics, as precisely enunciated by Fowler and Guggenheim in 1939, states that it's impossible to reduce any assembly to absolute zero in a finite number of operations. This means, in practice, absolute zero is an unattainable goal. So what happens within this quantum vacuum? Photon-photon interaction, for example, can only occur through interaction with the vacuum state of another field, like the Dirac electron-positron vacuum field. This phenomenon is closely tied to vacuum polarization. Gerald Miloni in 1994 pointed out that all quantum fields have zero-point energies and vacuum fluctuations. Essentially, each component field, whether it's the electromagnetic field or the Dirac electron-positron field, contributes to the quantum vacuum in its unique way. One of the most intriguing manifestations of vacuum electromagnetic fields is the Casimir effect. Imagine placing two uncharged conductive plates very close to each other in a vacuum. You'd observe an attractive force between them. This effect is often attributed to vacuum fluctuations. However, Schwinger, Dirac, and Milton in 1978 proposed that the Casimir effect can be explained by considering the vacuum as a state where all physical properties are zero. They suggested that the observed phenomena result from the electron motions on the electromagnetic field known as the source field effect. Miloni further argued that the measurable physical effects usually attributed to the vacuum electromagnetic field, like the Lamb shift, van der Waals forces, and the Casimir effect, require contributions from the self-energy of electrons or their radiation reaction. This perspective aligns with Jaffe's statement in 2005 that the Casimir force can be calculated without reference to vacuum fluctuations and vanishes as the fine structure constant alpha approaches zero. Let's delve into how the quantum vacuum state isn't just a laboratory curiosity, but a fundamental aspect of our universe. The vacuum state is associated with a zero-point energy, the lowest possible energy state, and this zero-point energy has measurable effects. One such effect is the Casimir effect, which can be detected in the laboratory. But the implications stretch far beyond. In physical cosmology, the energy of the cosmological vacuum appears as the cosmological constant. Imagine this. The energy of a cubic centimeter of empty space has been calculated to be 1/trillionth of an EARG, or about 0.6 electron volts. This minuscule amount might seem insignificant, but it holds the key to some of the universe's most profound mysteries. A potential theory of everything must explain the energy of the quantum vacuum state and how it correlates with the physically observed cosmological constant. For a relativistic field theory, the vacuum is Poincare invariant, a principle that follows from the Weightman axioms. This invariance implies that only scalar combinations of field operators have non-vanishing vacuum expectation values, or VEVs. Interestingly, the VEV may break some of the internal symmetries of the field theory's Lagrangian. When this happens, the vacuum has less symmetry than the theory allows, leading to a phenomenon known as spontaneous symmetry breaking. This is not just a theoretical construct, but a cornerstone in our understanding of particle physics and cosmology. Just when you thought the quantum vacuum couldn't get any more fascinating, let's dive into the quantum corrections to Maxwell's equations and their extraordinary implications. In the quantum vacuum, even the classical laws of electromagnetism get a subtle upgrade. Quantum corrections to Maxwell's equations introduce a tiny, nonlinear electric polarization term in the vacuum. This means that the electrical permittivity, denoted by epsilon, can deviate from its nominal value E in the presence of strong electric fields. This phenomenon is elaborated on in the works of Dietrich and Geers. According to the theory of quantum electrodynamics, QED, the vacuum itself should exhibit a slight non-linearity. Imagine this. In the presence of an extremely strong electric field, the vacuum's permittivity increases just a tiny bit compared to E rho. Experimental efforts are ongoing to confirm that a strong electric field could also modify the effective permeability of free space, becoming anisotropic. This means it would slightly decrease below m-rho in the direction of the electric field and slightly exceed m-rho in the perpendicular direction. But there's more. The quantum vacuum exposed to an electric field can exhibit birefringence for an electromagnetic wave traveling in a direction other than the electric field. This effect is similar to the Kerr effect, but happens without any matter being present. This tiny non-linearity can be understood through the concept of virtual pair production. The electric field strength required to make these non-linearities significant is predicted to be enormous, about 1/32 VM, known as the Schwinger limit. The equivalent Kerr constant for this effect is estimated to be about 10 circumflex 20 times smaller than that of water. While experimentally measuring such an effect is incredibly challenging and has not yet been successful, it opens up a new frontier in our understanding of the quantum vacuum and its interaction with electromagnetic fields. So, as you can see, the quantum vacuum is not just empty space, it's a dynamic, ever-changing field with properties that continue to surprise and intrigue scientists. Keep questioning, keep exploring, and stay tuned for more cosmic insights.